All right, so hello. This is going to be lesson number 2, so you should only be watching this one after you've watched the first one, which was on statistical questions. And so when we ask a statistical question, it's because we want to collect data. And when we collect this data, it's because we want to do something with it. We want to learn from it. We want to be able to predict things, or just have a better understanding of whatever it is that we're taking that data on. And to be able to do that, it's easier when the data is organized in a good way. So, if I went and asked you all your shoe size for whatever reason, if I just kept it in the list in the order of the numbers that you guys gave me and tried to analyze it from there, it'd be kind of hard just to have a long list of numbers. So there's a lot of different ways that we can organize this data to help us be able to interpret it and understand it better. And so the first way we're going to talk about is with a line plot or a dot plot. So your IXL skills are going to say line plot, but your Go Math book, so if you look at that online, says dot plots. So we'll kind of go back and forth between the two terms. But a line plot or a dot plot is a visual display. So like I said, we're going to organize this information, this data we're collecting, visually though. So it's a visual display in which each value of data, each point of data, each number we collect is represented by a dot, so literally a dot, or a line. If we're talking about a line plot, it'll be a little X, which you guys have seen in elementary school. You should have. Above a number line. So we're going to use a number line to create our dot plot. Line. There we go. Line with a number line. So a dot plot does show the frequency of each data value. And what that means is the rate at which something occurs or repeats. So that's one of the unique things about a dot plot or a line plot, and one of the reasons that we would use it over some of the other visual representations we're going to learn about, is that it does show every single piece of data. So sometimes that's going to be more helpful, sometimes we're not going to want that. It all depends on the data set you have, the numbers you have, and kind of what you're looking to learn from it. So for an example, first we're going to talk about just how to create a line plot or a dot plot, what it looks like. So a baseball team records the number of runs they score in each game for several weeks. And so like I said earlier, if we just, we're taking this data for some reason, they want to look at the numbers of runs that they've scored to see how they're doing. And it's kind of hard to figure out what's kind of going on just looking at this list of numbers. It's not in any order. It's not organized in any way. And so it's most likely that something's going to be overlooked, something's going to be missed. So if we can create a dot plot, it's going to be a little bit more helpful. So you're going to start off with your number line. I will give those to you for your practice problems. Let's see if that can focus. All right, that's what we're working with. I think it's because it's dark outside. I should go to bed. So run scored. So 6, which will be here. 1, y'all are going to have to just bear with me while we make this. 3. And so I do want to note that I'm crossing off each number as I make a dot just to kind of keep track of my data. So I know that I haven't repeated a dot or that I don't miss a dot. Something I also want you to note is if you're making this on your own, try to keep the dots the same size and the same distance apart. Otherwise, some of the things that we're going to be looking at aren't going to actually be visible. So I'll come over here for a little example. If we had, for instance, like big dots, they're pretty far apart, so that'd be 3, right? But then if we do like a bunch of tiny dots close together on the other line, well, that's 5 now, but they're the same height, and so it's going to be kind of hard to tell which ones there's more of without counting. And then also, this stands out a little bit more because they're bigger and bolder, so does that mean something? But it doesn't, so really make sure that you're kind of doing what I'm doing, keeping all of our dots the same distance apart and all the same size so that we can accurately read our dot plot. All right, cool. So we can use this, like I said, to look at a couple different pieces of information, which we're going to do with another example. But it's truly that easy to make a dot plot. You take your list of numbers, you have your number line, and for each data value, you put a dot for that data value. So when we do that, we can interpret those values. So whatever our dot plot looks like, how many numbers there are, how many dots there are, things like that. We can answer some questions about the data using the dot plot. So customers at a pizza shop were asked how many toppings did you add to your cheese pizza? And so I already created that dot plot for you. Technically, I guess this would be a line plot with the X's, and so this is what you're also going to see opposed to the dots. I think IXL uses the lines, but they're truly the same thing. So as you can see, the options were 0, so they just got a cheese pizza, 1 topping, 2 toppings, 3 toppings, or 4 toppings. And so if you're asked some questions about just the values, just the numbers in the data, we want to make sure that we're interpreting the dot plot correctly, because there are 2 sets of values here. There's the numbers that are the answers to the question, and then there's the numbers that relate to kind of how many responses we got, because we are talking about that frequency, like we said earlier. How many times does a data value occur? So what's the greatest number of toppings ordered? So since we're specifically asking about the number of toppings, that means we're talking about these numbers here, the answers to the questions. So the greatest, obviously, is going to go to the far right on our number line, so 4. So if we, well, I'll go back to that in a second. So the next one, what number of toppings was ordered the most? And so, like I said, be careful when you're reading these questions, because most and greatest sometimes can be synonymous. But here we're asking what number of toppings was ordered most. So which answer was said the most? And we can look at that by looking at our dot plot or line plot and how many dots are on each line. And if we're looking at the most, then we want to know the most, the response that was given the most, which in this case is going to be 1, because there's the most number of X's on that line. Okay, so what I was going to do, I want to come back to that baseball question and use it to talk about it as well, these questions. So these are the 2 questions for this scenario. The greatest number of runs. So what is the number of runs that they scored that was the greatest? So that would be actually on the number line. For this to the right, is that your left? You're right. So 11 would be the answer to that question, whereas the number of runs scored the most, so what was the answer that was given the most often, and that is going to be the one with the most dots. So not the greatest number on the number line, but the greatest number of dots. So this one is going to be 2 runs. And then again, like we said, we're talking about each data value in this scenario, so we can find out actually the total number of games. We can just, that's literally just counting. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 19 total games because there are 19 dots. And we can say that as well about the pizza situation. How many customers were surveyed? We can find that out by counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 customers. I feel like I counted wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, we're good. Yeah? All right, so that is how we can just kind of use the data from the dot plot just as it's given, just numbers, just looking at those kind of quantitative amounts. Quantitative means literally amount. So the other thing we can do is look at the data's distribution. So important word there. We've talked about this one a lot. So when you distribute something, remember that's like how you pass it out. And so when we use the distributive property, we're passing things out evenly, okay? But if we're talking about data, all of our data is not going to be shared evenly, right? So if we go back to the pizza, it kind of is, right? Everything kind of has around the same amount. It's pretty even across the board. But if we look back at those baseball runs, this is definitely not distributed evenly, right? It kind of goes up and then comes down, and then this guy's way out here. And so that's kind of what we're going to talk about too, because when you look at a dot plot like this, especially comparing topics or comparing dot plots of similar data sets, it can kind of help you make a lot more inferences about what you're doing or what you're collecting data on. So when we look at the distribution, we're going to focus on three things: the spread. So literally, like, how is it spread out? The shape of something. Literally, we're going to talk about like some math vocab about the shape of a dot plot or a line plot, and the center. And so we know the center means the middle. And so we're going to talk about how we can look at the center of the data on the dot plot. So I've got two dot plots here. They go from 0 to 8, both of them do. And they also both have 15 values. I counted ahead of time, and I promise I counted that one right. Okay, so same number of data values, same kind of range of numbers, 0 to 8 on our number line, but these two dot plots look very different, right? These are kind of all grouped together. This one goes up at the top here, and it's kind of right in the middle. This starts low, there's this guy out here alone, and it goes up. And so that kind of says a lot depending on what this data was collected from. So those are the things we're going to talk about. So again, least to greatest. They both go from 0 to 8 on the number lines, but that's not what we're looking at, because you can make a number line from anything. We want to look at the least and greatest data values. So for this one, our least is 3, and our greatest is 7. Whereas here, our least is going to be 1, and our greatest is going to be 8. So think about like if you took like a test in class or something, least and greatest would be important there too, right? What was the lowest grade? What was the highest grade? If the lowest grade was a 60 and the highest was a 90, then that means everybody passed, everybody did good. Whereas if the lowest was like a 20 and the highest was a 100, then everybody did a lot different. There'd be some people for sure that need some more practice, need to go over that topic again. And so when we talk about greatest, that means the greatest value in the data set. Whereas we have another part of it, and so this kind of goes along with the shape, the peak. So think about the peak of a mountain. It's like the very tippy top of the mountain. So for the peak of a dot plot, we're going to look for the tippy top of the dot plot. Where is the tallest line of dots or X's go to? So for this one, it's going to be 5. And for this one, it's going to be 8. Because those are right up there at the top. And so again, that kind of says a lot about the data if we look at just these two pieces we've analyzed so far. Least to greatest is 7, and then the peak is 5. And so 5 is right in between 3 and 7. So that means the peak is kind of right in the center of the whole data. Whereas over here, least to greatest, 1 is the least, 8 is the greatest, and then 8 is the peak. So 8's not only the greatest value, it's the highest number of responses. So we can already kind of guess and think about the shape of the dot plot. We're going to add to that a cluster. So think about like a granola cluster, right? It's like groups of granola. So we're going to look for our dot plot, a cluster of data values. So is there anywhere on the line plot that a bunch of data values are grouped together? So there doesn't have to be one. So for instance, this one we could say that the cluster is from 3 to 7, which is the least and greatest. So all of the data is just clustered together. Whereas this one, there's a very clear cluster, say that 10 times fast, because this guy's out here alone, and then all the rest of the data is off to the side. So there's a cluster here from 5 to 8. And so again, this kind of works with these other 2 points we've talked about, where we can see that our data is increasing as the values increase. So the number of responses increases as the actual values increase. And these clusters play onto something else. So this is actually a vocab word. You're going to have an IXL skill devoted solely to this. So outliers. It's exactly as it sounds. It lies on the outside. So if there's an outlier, it means that there is a data value, there is a number that is much less or much greater than the rest of the data. So for here, we don't have any outliers because they're all from 3 to 7. There's points the whole time. Whereas from here, this one's at 1, and then we don't have another data value until 5. So we are going to have an outlier here at 1 because all this data is over here together, and he's kind of out here on his lonesome. So think of like an outsider. Somebody's an outsider. It's kind of like they don't fit in. Same thing with an outlier. It's a data value that doesn't really fit in with the rest of the data. And then with all of these things going together, so looking at where our least and greatest is, kind of seeing that for this one, the peak's in the center. It goes up. It comes back down. It's symmetrical. No outliers there. Go up and down. So you guys know what symmetry is. Letter S is symmetrical, letter O is, the letter L is not. And when we're working with data on a dot plot, it doesn't have to be exact. This one has 4, this one has 3, so it's not perfectly symmetrical. But if anything, looking at this one compared to this one, this is way more symmetrical, whereas this one starts low, stays down, and then just kind of shoots up really quick. And so kind of going back to that test score example, you know, if I said, well, the lowest grade was a 60, but there was only one person that got a 60, and then everybody else got between like an 80 and a 90, then it would just be that one person that would, you know, again, kind of lying on the outside, 70 to 80 or 80 to 90. That means still everybody did fairly well. Whereas if we said it was from 60 to 90 and the data was kind of symmetrical or spread out evenly, then that would tell you more people got 60s and 70s and 80s and 90s within that range.